Okay, good evening, everyone. It is my pleasure to introduce André Chailloux, who is from Inria, Paris, and he's a quantum cryptography expert, and he will talk about post-quantum cryptography. Please, André, the stage is yours.
Hi, Jenny. So thank you for the invitation. It's a pleasure for me to be here. And so today, I'm going to talk about post-quantum cryptography, so a little bit generally what this topic is about, and then some of my own research in this topic, and more precisely, lattice sieving via quantum random walks. And so this second part is joint work with Johanna Loyer. I cannot, sorry. Okay. So yeah, sorry about that. So as I said, my presentation will have two parts. The first part will be a generic part on post-quantum cryptography, what the field is about. So it will be a quite short part. It's more like maybe a long introduction to like the like for the topic, like for my talk. And then I'll present the quantum algorithm, like this lattice sieving, and so it's the quantum algorithm for the shortest vector problem. So quantum computers, so is it a threat for cryptography? So as you know, many cryptographic schemes rely on the hardness of computational problems. And so we have tons of examples of this statement. For example, in public key cryptography, the security of the RSA encryption scheme relies on the hardness of solving the factoring problem, or a variant of the factoring problem. Also, the Diffie-Hellman key exchange, or the Schnorr signature scheme, they both rely on the hardness of solving the discrete logarithm problem. And so there are many, so these are like very kind of standard kind of encryption schemes, signature scheme, key exchanges. And there are many of those, like tens, hundreds of those, and they all rely on the hardness of some computational problem. And problems that we believe are hard against classical computers. But of course, when the quantum computer arrives, then we have to reassess everything. And for example, the examples I gave you, the factoring problem or the discrete logarithm problem, they can be solved in polynomial time with a quantum computer. And this is one of the main applications of Shor's algorithm. And also, all of cryptography based on elliptic curves, for example, also can be attacked with Shor's algorithm. So it shows already that there are problems with all these kind of cryptography, and that we have to do something about it. There are other primitives. Of course, not everything seems to be broken by quantum computers. For example, if we consider hash functions such as SHA-3 or symmetric encryption such as AES, these seem secure even against quantum computers. So when I say that it's secure against quantum computers, it doesn't necessarily mean that we can use it as it is without any changes, but it means that we can easily adapt those functions by maybe adding a little bit of key or increasing the size of the hash functions in order for them to remain secure against quantum computers. So as a warm-up, as an example, I'll present what is the quantum security of hash functions in the quantum world. So we start from a hash function h. So maybe this is not the most standard, but this is what makes the discussion the easiest. So here we start from a function that has n-bit inputs and n-bit outputs. And we want the function h, or hash function, to behave like a random function. And so you're given this classical description, so the circuit description of a function h, and you want it not to have too much structure that you can exploit, and that it behaves like a random function. And so some of the properties we want from a hash function are the following. The first one is that it's hard to invert, that it's a one-way function. So said h, you have an efficient description, so you can compute it easily, but it should be hard to compute a pre-image, to compute the inverse. So if you're given y, it should be hard to find a pre-image x such that h of x equal y. Then there are two other properties that we want from a hash function. The first one is the second pre-image, is given x, you need to find an x prime different than x such that h of x equal h of x prime. So this is very similar to the one-wayness property, but you're not only given y, but you're also given a preimage x of y, and what you want to find is a different preimage x prime of y. So x prime such that h of x equal h of x prime. And then there's a third property, which is also extremely useful, which is collision finding. So it should be hard to find 2 points, x and x prime, which is different from x, such that h of x equal h of x prime. So this is similar to the second preimage problem, but here you have the choice in both x and x prime, whereas before you were given x and you were supposed to find x prime. And typically, like collision finding, this is very useful when you want to construct commitment schemes, for example, out of hash functions. Then you want it hard to find a collision, and typically, if you want 128 bits of security, well, you want that an adversary can find a collision with, he needs time 2 to the 128 time in order to find a collision. Okay, and so what are the classical security of a hash function? So if h is a random function, what is the complexity of solving those problems? So for one-wayness, then we cannot do much better than try all possible values of x, because we cannot extract any structure, let's say, from the circuit. And so this takes time 2 to the n. Say 2 to the n, it's order 2 to the n. Of course, I will only talk asymptotically. I will omit the O factors and these things. So one-wayness, the best thing you can do is try all possibilities, takes time 2 to the n. The second preimage, the same thing. The only best thing you can do is try all possible values of x prime, which are different than x, and hope to find the second preimage. It takes you time 2 to the n. Collision finding, you can do much better. You can use the birthday paradox. So here the O tilde hides some polynomial factors in n. And actually there are some ways to, even if you know nothing, you can only apply the function h as a black box. You can use the birthday paradox in order to find a collision in time 2 to the n over 2. So very briefly, how do you do this? You pick 2 to the n over 2 random different input from x1 to x to the 2 to n over 2. You compute h of these values. So you have a big list of outputs of size 2 to the n over 2. You sort that list with, so this takes you O tilde of time 2 to the n over 2. And then each time you query a new input x, a new random x, you want to know whether h of x is in this list. And this, you can do it efficiently via dichotomic search because the list is sorted. And so somehow in time polynomial in n, each time you have a new x, you can test whether h of x is in this list. So what you can do once you have this list of size 2 to the n over 2 is check new elements that you haven't queried before. And each of these new elements will have a probability 2 to the minus n over 2 of being in the list and of provoking a collision. So you only need to find 2 to the n over 2 such new queries in order to find a collision. So these are very standard security notions for classical hash functions. And typically, if you have a practical hash function that doesn't satisfy these 3 criteria, then you consider it's not as good. It's not as good as a truly random function. And so how does it work in the quantum regime? So in quantum security also, we can have exactly the same analysis. One-wayness, you try all possible values, but you apply Grover's algorithm, so you gain a square root. Second preimage, the same thing. You apply Grover's algorithm, you gain a square root. And collision finding, you can do the equivalent of the algorithm I presented you for the classical setting, and it does better than the classical setting, and you can find a collision in time 2 to the n over 3. So, for example, with the BHT algorithm, so the Brassard, Hoyer, and Tapp algorithm, or Ambinis's algorithm that uses quantum random walks. So what's interesting here is that you can do better than in the classical setting, but for example, for the collision finding, you don't have a full square root advantage. And so this means that if you want 128 bits of security, so if you want all of these operations to take at least 2 to the 128, it means that classically, you need to take n equal to 256, and quantumly, n equals 384. And so this is what I meant, and this is what we mean when we say that hash functions remain secure in the quantum regime, is that not with the same n, you need to increase the size of n in order to have the same security, but you can do it with not a too big loss, something which in practice, this is something that we can do using hash function with larger output space. Input and output space is not something which is very harmful for the efficiency of our cryptographic schemes. Okay, so this was like one example of what it is to assess the security of some cryptographic function schemes, protocols in the quantum world. And so the goals of post-quantum cryptography is to do this for all existing cryptography, to see like how does quantum computers affect all our schemes. So there are two subpoints here. The first one is to say, well, we need to look at quantum algorithms. So what I showed for hash functions before is actually optimal if you can only query the function h. But for example, if I give you a concrete function h which has a circuit, maybe there is a structure that you can exploit. And sometimes there are some functions which have a structure that you can exploit in the quantum setting and not in the classical setting. And so each time you have a new function, each time you have a new computational problem, like you don't have like general laws or general rules. You have to look each time and look how it behaves. Sometimes it behaves well, as I showed you in the previous example. Sometimes it behaves very badly. For example, when you base your security on the hardness of factoring, then you have Shor's algorithm that breaks it. But you have many other examples of schemes, and each time you have to look whether quantum computers break the scheme a lot, or you just have slightly better attacks, Grover attacks, or quantum collision attacks that make that you have to change a little bit your parameters in order to remain secure. There's a second aspect in assessing the security of cryptography is security proofs. So security proofs is the implication that if you have a computational hard problem, then the cryptographic scheme you build from your computational hard problem is secure, right? And what is quite surprising is that if you want to do this the implication in the quantum setting, you cannot directly adapt the proof from the classical setting, even if your underlying computational problem is hard for quantum computers. You still need to prove this implication, and sometimes it's tricky, sometimes it's wrong, and so you need to look again, not only at the hardness of the computational problems, but also this implication, the security proof implication, also in the quantum setting. And then there's another aspect of post-quantum cryptography, which is also very important, is to provide new designs for cryptographic schemes from quantum secure assumptions. So we did this first step. We tried to attack some problems, and we believe that they're hard against quantum computers. Great. Let's build some encryption schemes. Let's build some signature schemes. And we know that the basis will be a hard problem for quantum computers. And then if we have techniques for quantum security proofs, then we can go from there and show that the design, the scheme is secure against quantum computers. And so it's an ongoing, so it's really an ongoing work, and there are a lot of things to do. And so these three aspects are like very important, and these are the three main aspects of post-quantum cryptography. And okay, so one thing that in post-quantum cryptography is that there is a big new interest in this topic. And one of the reasons that, one of the events that fueled this interest is that the NIST, the National Institute of Standards and Technology, made a competition to standardize post-quantum cryptography. So in 2017, they said, okay, we need to standardize some schemes, so some encryption schemes, some key encapsulation mechanism, and so signature schemes, because there are a lot of things going on, but we want something that a lot of people have looked at, that are efficient, and that we have the strong belief that they're secure against quantum computers. So they started in 2017, and currently we're in the round 3 of the standardization. So there was a round 1, so there were like many candidates, so there are like maybe 40, 50 candidates. Then there was a round 2, there was half less, and then there was round 3, and there are just a few finalists in each of the categories. And what's interesting is that there are a lot of different computational assumptions for these schemes. So, for example, there's lattice-based cryptography, so we'll talk about it a lot in the part 2 of this talk. code-based cryptography, so cryptography based on the hardness of decoding random linear code, cryptography based on isogenies, multivariate polynomials, also just on hash functions as well without any specific structured problem, and several other ones. So there's a big diversity in the computational assumptions, and there are many designs from many different problems, but there's not that much study of quantum algorithms for these problems. So that's something also that's interesting, and something that that should be nice, that this is really a topic that is that's interesting, is to look at the quantum algorithm for all of these problems. So okay, so this was the end of the first part. So just this kind of long introduction, and now I'll talk about lattice sieving via quantum random walks. So this is a paper which is joint work with Johanna Loyer, and we put that paper in May on the archive. So if you want, you can look it up if you want some more details that I didn't put in the talk. Oh, so lattice-based cryptography. So it's one of the main proposals for post-quantum cryptography. And many of the finalists of the NIST competition are from lattice-based cryptography. And to say it short, it's the most hyped computational assumption in the post-quantum, and not only in the post-quantum, because from lattice-based assumptions, you can do many things. You can do homomorphic encryption, you can do indistinguishability obfuscation, you can do a lot of kind of these modern cryptographic tasks, which are quite complicated. Actually, from lattice-based cryptography, you have enough structure that you can do a lot of cool things, and the problem still seems to be hard. So, okay, so now let me define here lattice-based cryptography. So a lattice, so we are in a large vector space Rm, and we construct D vectors, which form a basis, so B1 through BD. And so the span of these vectors will form a D-dimensional vector space. We will only be interested in this D-dimensional vector space. And so we have these vectors, these basis vectors, and the lattice L of B will correspond to all the linear combination of these basis vectors. So it will need the sum over I of lambda I bi for any lambda I in Z. So we have an infinite number of lattice vectors because the lambda I are unbounded. And so this is the lattice. And so the goal is to find the shortest vector of this lattice, non-zero vector of the lattice. Okay, and so if I give you an example, so here if we just have only two vectors, B1, B2, the black dots are the points of the lattice, and the red arrow would be the shortest vector of the lattice. So, okay, in 2 dimensions, this looks kind of very easy, but okay, you have to imagine dimension D, which is quite large. So in hundreds, like 300, 400, like that. In the actual schemes, like they use D in the hundreds. And the basis vector, you don't have an orthonormal basis. So the vectors B1 through BD, some of them are smaller than others, and they're not orthogonal. So, you cannot, so they're far from being orthogonal. They don't have the same norm. They're messy all around. And so it's very hard kind of to construct, like if you had an orthonormal basis, then the shortest vector would be the smallest vector of the basis. That would be very simple. But these vectors, because they don't form an orthonormal basis, it's actually hard to find the shortest vector of the lattice, or even a vector which is close to which is not too large. And this is already quite complicated with this. So this is the shortest vector problem, and there are several problems that you can define on lattices. There are several hard problems, and so this is one of the main ones. And so why do we want to solve this problem? Why this problem is interesting? There are many other problems, as I said, that can be directly derived from the shortest vector problem, like the short integer solution problem, learning with errors, the specific problem using ntrue. And many quantum-resistant crypto systems are based on these problems. So dilithium, Falcon, ntrue, Kyber, Saber. So these are all or signature schemes or encryption schemes or key encapsulation mechanism. And these are typically the names of the NIST finalists. So yes, and the security of these crypto systems is directly related to the complexity of solving SVP. Why is that? is because like even if they don't rely on SVP directly, the best algorithms to attack these schemes is called the BKZ algorithm, and it uses as a subroutine an instance of SVP as the shortest vector problem. So, and it's the main component. And so if you can improve this main component of this algorithm, which is the best attack, then directly you can improve the best attack on all these crypto systems. So really like all these crypto systems, what they say is that they look on the best attack on SVP and they say, okay, from there, this is how we assess the security of our scheme depending on these attacks. So it's arguably the most important problem in lattice-based cryptography, which is arguably the most important family of problems for post-quantum cryptography. So, you know, it's a good choice. It's a good thing, you know, to attack this SVP. And so the goal of the talk will be to present the quantum algorithm and also like our improvements on this problem. Okay, so SVP. So there are a lot of different ways of tackling SVP, and here I will present one of the methods, which is currently the most efficient method for solving SVP in the theoretical setting and also in the practical setting, is the sieving algorithm, which is what you saw in the title. And so here I will present one formulation of sieving algorithm, which is due to Nguyen and Vidic from 2008, so the NVC. So what is the idea of this NVC? As an input, we have a list L of n lattice vectors of norm at most R. So R, at the beginning, think of R as something which is quite large, right? So it's much, much larger than the shortest vector. So they're not very good, let's say, if good we mean short, then they're not very good vectors. So they're more of norm at most R. We have a variable gamma, we have a parameter gamma, and the output will be a list L prime of n lattice vectors of norm at most gamma R. And so if gamma is smaller than 1, then from a big list of vectors, we manage to find a list of vectors of the same size, also of n lattice vectors, but of smaller norm. And so, of course, if we repeat this enough times, then at some point we'll have n list of very small vectors. Of course, this doesn't work if R is very close to the shortest vector. At some point, you cannot shrink it infinitely, but for a very long time, you can shrink lattice vectors into lists of smaller lattice vectors. And how do you do this? Well, the idea is very simple. You take each pair of the list L, and you compute the difference. So for each VW, you compute V minus W. And if it's smaller than gamma R, you add it to the list L prime. So here is an example of V and W, which are the sphere of size R, and V minus W, if it's smaller, you add it to the list L prime. So a few remarks is that we start from, okay, so first, how do we initialize? So we have ways of initializing. You don't take random lattice points, you do something slightly more clever so that it's well distributed on the sphere. But, you know, so you use Klein's algorithm, but, you know, R will still be very, very large. This is it's not something, so the initialization doesn't need to compute very short vectors. So first thing is that if you compute the difference of two vectors, then if the two vectors were in the lattice, then the difference is also in the lattice, because we call that all linear combination is the, you know, a lattice point is any integer combination of the basis of the basis, and so V minus W is also an integer combination of the basis points. And the second, what is the criteria for V minus W to be smaller than gamma R? So here we'll consider gamma, which is very close to 1, slightly smaller than 1. It will be enough to have gamma, which is very close to 1, and to iterate this enough times. And for gamma, which is very close to 1, then the 2 points V minus W is smaller than gamma R if their angle is smaller than pi over 3. So this is a computation that you can do. So this is something that I haven't said, but so we are in a Euclidean norm or in 2 norm. And so in the Euclidean norm, this property holds. So what's interesting is that it's easy to compute because, for example, it's independent of R. No matter what R you have, if the angle is smaller than pi over 3, then the v minus norm of v minus w will be smaller than r. So these are like kind of some first geometric statements to understand what's going on. And okay, so now that we have this geometric statement, which value for n? As we said, why why do we need to start with a lot of points? So, well, as I said, the probability that a pair VW, the fact that the V minus W will be in the list L prime will be of norm smaller than gamma R. So this we say, if this is the case, we say that this pair, the pair of vectors reduce. And so, as I said before, the probability that a pair of vectors reduces is if their angle is smaller than pi over 3. And if we assume that the vectors are uniformly on the sphere, distributed on the sphere, then this probability, we can use a geometric argument, that it's asymptotically equal to 3/4 to the power d over 2. So it's exponentially small in d. And because they are order of n squared pairs, we can construct, if you're order of n squared pairs, this procedure will allow us to construct up to p times n squared pairs in L prime. So if we take n, which is 1 over p, or slightly above 1 over p, we'll be able to find enough pairs that reduce so that we can construct n reduced vector in the list L prime. And of course, if we can do it once, then we can do it twice, 3 times, 4 times, and we can repeat this enough times in order to have small vectors. And so 1 over p, it's exponential in d, is 2 to the 0. More or less 2 to the 0.2 times d. And this is still tractable, right? It's exponential in d, but as I said, like if there are some crypto systems that use a d equal 250, for example, maybe 200, maybe not 250, but less than 300. So, you know, it's values which are like between 2 to the power 50, 2 to the power 60. It's a lot. It's a lot of points, and it's at the limit of what is tractable. But you know, and so this shows that that you know that it grows exponentially. But you know, up to certain values, this is still something that we can do, that we can enumerate. Okay, and so what is the complexity of sieving with this algorithm? So each step of sieving, classically, I said we have to check all pairs. And so this time order of n squared. We have n points, we need to check all pairs. So it takes 2 to the 0, 41d. Quantum complexity, this can be sped up with Grover's algorithm. We need to find n out of n squared pairs that reduce. And so it takes us time ordered n to the 3/2. And these are the complexities that I gave for one step of the sieving. And actually, even by taking gamma, which is goes arbitrarily close to 1, actually we only need to repeat this polynomial poly d time. So basically, we take gamma, it is 1 minus 1 over d. It will not change a lot this computation. And by repeating polynomial in d times, the sieving step will have at the end many points which are small and from which we easily be able to extract a small vector in the lattice. So the number of sieving steps is polynomial in D. It doesn't change the asymptotic complexity, right? When you have something which is exponential, if you had a polynomial factor in front of it, then you know for our analysis at least you can ignore it. So really, what we'll be interested in is to compute the complexity of one sieving step. Okay, so this was looked at the shortest vector problem. So we wanted to find the short vector, and we said, okay, we construct, we do have the sieving, we construct from n points, and we try to find some pairs that reduce. And this is a little bit, in some sense, it can be seen as a little bit naive, is because we check all pairs. And so the idea of locality sensitive filtering is that we will only check pairs of vectors which believe are already close to each other, so that they have more chances of being really close. So how do we do this? We will introduce a notion of filter. So a filter of center S and angle alpha it maps a vector V to a Boolean value 1 if the angle between V and the center is smaller than alpha, and 0 otherwise. So the filter is basically the green region. And if a vector V has angle less than alpha with S, then we say that it is in the filter. Otherwise, we say it's not in the filter. So V is in the filter, W is not in the filter. So this is the definition of the filter. And okay, before I go there, and so basically the idea, then I will go a little bit more in detail, is that we will put all the points in our list L in some of these filters, and we'll only check the pairs within those filters. And basically, if 2 points are in the same filter, then from a triangle inequality, we can say that they have more chances of being close to each other where if they were random points on the sphere. So this is the idea that we will use in order to improve the sieving algorithms. Okay, so what is the general structure of sieving with locality-sensitive filtering? So this is the general thing. Then I will go through some of the steps, especially the third step. I will go more in detail. But so basically, first what we'll do is that we'll generate filters all over the sphere. And this, so basically what we'll do is that we will try to put a lot of filters all over the sphere. And you know, we want them to cover more or less the sphere, and we don't want the filters to touch each other too much. But you know, you cannot do this perfectly, but let's say approximately that you can generate filters such that they recover the whole sphere and they don't intersect. And what will be important is that the centers of the spheres will be words from a code. And why do we do this? Is that such that each vector will be able to say in which filter it is. So in this ideal case, if they recover the full sphere and they don't intersect, each point will be in exactly one filter. And if we use the center of the filter as words from the code, we can use a list decoding algorithm to say in which filter it is. So I will not go in detail in how you do it, but assume the sphere is recovered with filters and that recover the whole sphere. And you can, for each point in the list, you can determine efficiently in which filter it corresponds to. So these first two steps, assume we know how to do them. I will not go too much in detail, but it uses codes and list decoding algorithms. And in the third step, well, we find all solutions within the filters. So you know, classically, we check all pairs and see if there is a solution in this pair, or quantumly, we do Grover search to find all solutions. And if we didn't find enough solutions, because as we'll see, like the fact that we only look for solutions that are in the same filter, pairs that reduce within the same filter, we won't find all the solutions in one iteration, then we'll iterate these 3 steps several times until we find all the solutions we want. And so what's really interesting is that this idea really improved the complexity. So the original NVC was 0.415D. And classically, we can go up to 2 to the power 0.29D time. And so this was, so there are several improvements in between that used some LSF, but basically the latest LSF algorithm has this complexity. And in the step 3, when you replace the classical looking for a solution by Grover search, you can reduce this to 2 to 0.265. And so, and in this work, and what I'll show later is that this third step, you can replace Grover search by a quantum random walk to decrease from this 0.265 to 0.2657 in the exponent. And then I'll show why it's actually useful to have this kind of improvements. Okay, so let's go. Our recap is that NVC using a quantum walk. Again, the NVC, we have a list of n lattice vectors. We want to find, construct a list L prime of n lattice vectors of norm gamma r with gamma going to 1. We had the 3 steps, and the main idea is to replace the third step of Grover search by a quantum random walk. So before I go into step 3, I will just very quickly repeat so that what are the 2 first steps. So I kind of repeat what's going on here so that you don't lose track of our algorithm. So you sample a code and generate the alpha filter. So here I only presented one code word, which is S. and the alpha filters. And so the alpha filter is basically everything which is below the dotted line. So from the dotted line to S. And the points are the points of the list which are in the alpha filter. And as you saw, I put all the points on the border of the filter. This is with high probability, most of the points will actually be on the border. This is because we're in D dimensions, and so by some geometric argument, this is something that you can show. And so we construct. So this is the example of one filter S and all the points around, and we construct many points S and with associated points from the list L. And so assume we have n to the power c vectors in each alpha filter. So the total number of points is n. And so in each filter, we'll have n to the power c vectors, with c which will be smaller than 1. So we have all of these vectors. And so what we'll be interested in is that actually, this is what we'll call the residual vectors, is that all of these vectors, because they lie almost all on the border of the filter, they have a component in S, which is the same, and then they have the second component, which is orthogonal to S, and which lies in this sphere of dimension D-1. And these are elements which are all orthogonal to S. And so this we'll call residual vectors, and actually we work on these residual vectors. And what's interesting is that, as I said before, points which are in an alpha filter have a greater chance of being reduced. Pairs that are in the same alpha filter have a greater chance of being reduced than random points. And so typically, if we have a pair VW, which is in the same filter, saying that their angle, okay, so theta is the angle between the two vectors. So saying that the angle between V and W is smaller than pi over 3 is equivalent to saying that the angle of the residual vector is smaller than some value theta star alpha, so which is a value that depends on alpha. I didn't put the formula is a bit complicated, but it only depends on alpha. But what's interesting is that this value theta star of alpha is much larger than pi over 3. Right? Of course, it's not pi over 2, but it's much larger than pi over 3. And that means that you have a much greater chance if you have two random residual vectors. There's much greater probability that they reduce than if you took any two random vectors. So this is really the interest of working with these alpha filters. Okay, and the step 3. Once we have all of these vectors in this, so let's say we have NC vectors in each alpha filter. So let's say we fix one alpha filter of center S. We have n to the power c vectors. We write each vector as the component to the center and the residual vector. And we look for all pairs of reducing vectors, and with this implication on the residual vectors. And so the previous algorithm uses Grover search. If there are S solutions to this subproblem, then this takes time, this quantity. So each solution, you can find it in time n to the power 2c divided by s, I mean the square root of this. And so to find S solution, you multiply this by s. And why is that? Is because there are n to the power 2c pairs. There are S solutions. So the Grover's algorithm, the time of Grover's algorithm is the root of this quantity to find one solution. To find S solutions, you multiply this by s. Okay. And so now I will talk about quantum random walks. Okay, so quantum random walks. So maybe you've seen in some courses quantum random walks and all of its application to algorithms. So I will just make a brief overview of random walks and quantum random walks.
Yes, you can be very quick. They had a whole course on that.
They had well, perfect. Okay, so I'll go, but you know, there's still some technicalities and so things which are specific to this. So you know, I'll still not go too fast. So, okay, so random walk. So you have a graph and you have a function that tells you have vertices, you have edges, and you have a function that tells you whether a vertex is marked or not. And so the goal is to output a marked vertex. And so I will present here the MNRS framework, so the Magnez, Nayak, Roland, and Santa framework. And so classically, what's the idea of the random walk is that you start from a random node, you perform 1 over delta steps, which is called the update, where delta is the spectral gap of the graph. You check whether the node is marked or not. And okay, and here there's a typo. This happens with property epsilon and not 1 over epsilon. And if not, start again. So we have the setup cost, which is the construction of the first node. Delta is the spectral gap of the graph. And the idea is that if you start from any node and you perform 1 over delta steps, you will arrive at a random node. So delta is strongly related to the mixing time of the graph. So you start from any node, you do 1 over delta steps. So a step is you go into a random edge, you pick a random edge around your node and go to the neighboring edge, to neighboring vertex. And so delta is the spectral gap of the graph. Epsilon is the probability, is the fraction of marked vertices. And so if you arrive at a random node, the probability that this is marked is epsilon. And if not, you start again. And so classically, the time is the setup time plus each time. So you perform 1 over delta steps. And so the update is the time that you need to go from one node to the other. So 1 over delta U to go to a random node, plus the time you need to check whether the node is marked. And you succeed with probably epsilon, so you repeat these steps 1 over epsilon times. And so there are many ways of doing classical random walks. And so the idea, what is nice here, is that in the quantum setting, you can adapt this and you can put roots in front of the epsilon and in front of the delta. And so this was the part of the MNRS framework for 2011. There are many other frameworks of quantum random walks, but this is the one which is used. And so which is used, for example, for collision algorithms and things like that. Okay, so we need to do a quantum random walk. So we need to have some vertices and we need to put some information on the vertices and we need to say, what does it mean for a vertex to be marked? So recall that we have our n to the power c points in our alpha filter and we want to find all reducing pairs. So in each vertex, there will be n to the power c1 vectors from the alpha filter, with c1, which is smaller than c. So a subset of all the points, we will put them in the vertex. Okay, what is a marked vertex? I will not say what it is yet, but it will be a subset of vertices which contain a solution. So what's a vertex which contains a solution is if you have a reducible pair, not in the n to the power c points, but in n to the power c1 points. So if from y1 to y to the n power c1, you have a pair that reduces, then I will call that a vertex that contains a solution. And ideally, we would like to mark all of those vertices, but actually it will be more efficient to mark less, and I'll tell you later why. So this is already in contrast. If you know, this is reminiscent, for example, to collision algorithm. If you know the quantum random walk, like Ambainis's quantum random walk for element distinctness or collision finding, it's exactly the same thing, right? You have your images, and then you take a random subset of your inputs, and you check whether there is a collision in this random subset, and you mark it whether there is a collision in this subset. So here it's very similar, but we don't mark exactly the same way. We'll mark only a subset of these vertices. And in this vertex, we will also add some additional data. So we have our n to the power c1 points, and we will create some other filters for these points, which we'll call beta filters, which will work exactly as the alpha filters. And again, we'll put this, so we said that they all lie in this sphere of dimension d-1. And we'll construct a code in this sphere of dimension d-1 and beta filters. So with centers, and we say that the point is in this filter if it has angle that moves beta with the center. And again, we want them to recover the whole sphere. We want them to approximately partition the whole sphere. And so we construct those filters, and then each point we put it in its corresponding filter. And the reason we do that is that this will help us to determine whether a vertex is marked or not. And also we add a bit that says whether the vertex is marked or not. This will be part of our vertex. So in the picture, in the bottom, you can see that the black points are the n to the power c points of the alpha filter. And the red points, for example, are the n to the C1 points. So we take a subset of the points. So in the vertex, you have the red points and the green filters associated to each point. Each point, we say, okay, it corresponds to this filter. So this is the information that will be contained in the vertex with the bit that says whether the vertex is marked or not. And we choose beta such that there is approximately one red point in each filter. So on average, there will be 1 point in each beta filter. Okay, so now I told you what's in a vertex. Now I have to tell you like the whole graph. So what are the edges of the graph? And so like in the collision finding, it will be on the Johnson graph. So the Johnson graph, the vertices, as we showed, it will be a set of n to the C1 points from the n to the C points of the current alpha filter. And two vertices will be neighbors if and only if they differ by exactly one vector. So here I show the picture of Johnson graph 5.2. And in our case, here is an example, is that we say, okay, on the left, we have one vertex with the 4 points. And on the right, we have a neighboring vertex because we could go from the left one to the right one by removing 1 point, so the bottom right red point, and by adding 1 point, the blue point, top left one. Okay, and sometimes it can happen that in each filter there are a few points, right? There's on average 1 point, but it doesn't have to be equally distributed exactly, right? There will be on average a constant number of points in each filter, but it doesn't have to be exactly 1. And now I can tell you how we mark vertices. We say that the vertex is marked if and only if it has a reducible pair within the same beta filter. So when we will check whether we have whether there are reducible pairs in our vertex, we'll only check within the same beta filter, which means that, again, we'll lose many marked vertices. We'll lose many vertices that contain a solution. It will only be a small subset of the marked vertices, but we'll see in a second why this is actually nice to do. So, as I said, so there's the complexity of one quantum random walk, so to find one solution. The setup is to construct the first vertex and compute their beta filters. So we have n to the C1 point, and as I said, each point, we can put it in its corresponding beta filter in time 1. So the whole thing will take n to the power C1. And also we check, for example, if there is, we also need in the setup the first vertex to see if there's a solution or not. So we can apply a Grover's algorithm, for example. We check all the pairs, it will also take time n to the C1. Then the update is how you go from one vertex to another by keeping all the information. And so we remove one vector, we add one new vector, and what we need to do is to compute the v-new find its beta filter, but also check whether the vertex is marked after adding the new point. And because you only need to check in its beta filter, and because there are only a constant number of points on average, the update will take time 1. And so this is what was important. If we marked all the vertices which had a solution, the update time would be much, much larger. And so there is a big issue in the update time of this algorithm. But with this technique, by only marking a small fraction of the vertices, you can have an update time which is 1. And now with this update time of 1 and this checking time of 1, the checking time is 1 because there is a bit in the vertex that says whether you're marked or not. So you just have to read that bit. So it's actually 1. The spectral gap of the graph is 1 over n to the power C1. This is a property of the Johnson graph. And the probability that a vertex to be marked, epsilon, is something complicated. It's something that depends on all of these parameters. It's a quite complicated formula. Is the probability that there are 2 points that are reduced and that are in the same beta filter. So we lose a lot. So epsilon with this trick is much smaller than it was before. So the quantum random walk will take more time. But the benefits surpasses this additional cost of epsilon. And so the time complexity is, as I said, this time complexity of the MNRS framework. Okay, so now if I recap the whole thing, what are the whole time complexity? Steps 1 and 2, we construct alpha filters, we sample the code, we construct alpha filters, we put all the points in an alpha filter, we have n to the c vectors in each alpha filter, we perform a quantum random walk to find all solutions in each alpha filter. And we repeat those steps until we get n reduced vectors. So the steps 1, 2 takes time n because we said each point we can put it in alpha filter in time 1. And then, as I said before, because we said that if we have n points at the beginning, we have n pairs that reduce, but they are not all from the same alpha filter. So actually, if we put the constraint that we only look for reducible pairs in the same alpha filter, we can only find less solutions. And so we find n to the power zeta solutions. So zeta is a parameter that depends on c and c1. So it will be less than 1. And so each solution is found in time, the time of the quantum random walk. And we need to repeat the whole process n to the power 1 minus zeta times in order to find n solutions. And so we have a formula that gives the total running time in terms of zeta and the SUC. Okay, so just maybe I'll put some numbers on these parameters so that you have maybe a feeling of kind of how these quantities behave, because I just gave like a theoretical kind of complexities each time. So the optimal parameters take C equals more or less 0.37, C1 equals 0.238. And with these parameters, if you do the computation, we have epsilon equal delta equal 1 over n to the power C1. And zeta equals this thing, which is n to the power 1 minus C1. Actually. So we did all this computation. So these are the parameters that will optimize. And so with these parameters, each term of the quantum running of the quantum random walk will run in time n times 0.238. And again, these parameters equalize the setup time, which is n to the power C1, and the second part, so 1 divided by root epsilon delta, which is also n to the power C1. So all of this is equalized. It's like Unbiased algorithm for collision. And the total running time is therefore n to the 1 plus C1, or to the 2 minus zeta. And it's n to the power 1.238, which is 0.257. Okay, so if you're interested in other kind of resource requirements, it uses some quantum random access memory, unfortunately, like in all quantum random walks, but it uses much less than the quantum running time. It also uses quantum memory, but also significantly less than the quantum running time. So these are like fairly achievable things if we have a full quantum computer. And it uses classical memory of size n, because we need to store, like when you have the list of points, we need to store these points at each Sieving step. So if you want not only the running time, but other resources that we use, memory resources, this is what we have. We also have some trade-offs. So if you want to use less quantum memory, can you have some improvements? The answer is yes. And it's fairly, it's fairly linear. Improvement we get time in terms of the quantum memory. If you want QRAM, also you can, if you don't want to use quantum random access memory or less quantum random access memory, we also have all the trade-offs. These are not exactly lines, but they're like very close to lines. Also, to make a synthesis of the trade-offs and our values and our results, on the left, it's the best classical algorithm. So the time is the exponent. So it's 2 to the power alpha times d. And so this alpha is always 0.29, 0.26, 25. And so on the total left, it's the classical algorithm. In the middle, it was the best known quantum algorithm. And on the right, it's our algorithm. And in between is all the trade-offs that we want, which are also okay. So this is the end of our quantum algorithm. And so in conclusion is that we reduce the exponent of quantum algorithm for XVP from 0.265 from 0.257. And concretely, that means that if you have a scheme that declared that it had 128 bits of quantum security, now with our new attack, it has only 124. Okay. So this can be fixed with a slight increase of the parameters of the scheme. But so that's what's interesting, right? So each time you propose a scheme, then you have a new attack that will break a few bits of security. And so this means that you have to change the parameters, and then there'll be a new attack. And so back and forth like this. And it's this back and forth which is really important in order to fully assess the security of a scheme. And at some point it stops, So here we gain 4 bits of security, and then the next, and at some point when the new attack only gains 0.2 bits of security or stuff like that, or 0.02, at some point it converges to something, and you say, okay, the problem is very hard. We don't know how to find improvements to this problem. So this back and forth is what is important. And so this work was one of the steps that allowed to say, okay, you lose 4 bits of security here, you need to slightly change your parameters. Okay, second conclusion is, okay, you can ask like how practical are these attacks? Again, it uses quantum random access memory, it uses some memory. So, but if you do post-quantum cryptography, you assume, you're conservative, right? You assume that a full quantum computer will arrive, and that we will overcome some technical difficulties. So there's no reason to think that if you believe that you should do post-quantum cryptography because like quantum computers will arrive, then you should definitely consider this kind of attacks. And so the second thing is that there are a lot of other problems. I said, there are different problems in lattice-based cryptography, but also in code-based cryptography, isomorphic-based, multivariate, hash-based. And people have looked at quantum attacks on all of these problems, but it's still a fairly new topic. And there are a lot of interest in finding quantum algorithms for this problem. So if you're interested in quantum algorithms, but you don't know on what problems to attack, then these are very good candidates. There's a wide variety of problems, so they're all quite technical. You need each time to understand well, like you need to understand lattices, or each time you need to understand kind of a new model. But it's very rewarding because if you can improve the best quantum algorithm for this problem, it's interesting not only from the quantum algorithm perspective, but also more broadly to the cryptography, to the post-quantum crypto kind of community, which is much larger, and there's much more impact in understanding the quantum security of these schemes. So, okay, thank you for your attention, and I will end up here.
Okay, thank you very much, André. It was a very nice talk. I enjoyed it a lot, and I hope our viewers will enjoy it as well. And thanks. This was a really nice example of how to actually present and analyze an algorithm that uses many of the things that we have still studied in the masters. Actually, I have a couple of questions, maybe to connect it a bit with reality. But before, maybe Jose Manuel had some questions. No.
No, I don't have questions.
Okay, let's see. So first of all, you kind of anticipated my question is about the feasibility in practice. But can you comment a bit more about this? Like, how different are these lattice-based classical schemes, right? From RSA. So suppose there is Shor's algorithm implemented. In order to break RSA 2048, you will need a certain amount of memory and time. I guess time will be shorter than this, but memory is quantum RAM and in general stable qubits are still a limitation. How do you compare, for example, for quantum storage, say normal RSA and lattice-based crypto?
Okay, so maybe just go back to maybe this will be the good slide.
Yeah.
So first of all, okay, so it's hard to compare, first of all, like polynomial time algorithm and small exponential algorithm, because in the end they're kind of the same thing, but it's a kind of it's just that they don't scale the same, but since cryptographers always go at the limit, this has to be 2 to the 128, then
Well, so actually for practicality, right, one can say, what is the dimension that actually classical schemes can use? What is the value of D, and how does it compare in practice?
Well, the first proposals were around 300. So
okay.
the best attacks are on 200. The best classical attacks are about D equal to 100. that use sieving, and the first proposed schemes are around 300. And so, okay, so there are a few things. The first thing is that in Schur's algorithm, you don't need quantum RAM. You need quantum memory, but you don't need you don't need a quantum reading tape or something weird like this. So, and this is a big drawback of all these algorithms that are based on random walks, or even without using random walks. Actually, if you just do Grover, because you need to do Grover on the list, so you have a huge classical list, and you have to access this classical list all the time. Actually, this is what requires quantum RAM. This is actually why the quantum RAM is larger than the quantum memory. Right. That you need quantum accessible classical memory in some sense, and so to that extent. So this is something that might be not very practical, but we don't know. Like, it's probably like a separate. You need a hardware breakthrough to do those. And it's not clear whether when you will have a full quantum computer, we will have solved this problem as well.
Right.
The answer is
there is a big advantage that this post-quantum crypto has compared to just RSA, for example.
Oh yeah. No, but I mean the scaling of RSA is horrendous. I mean, if you want it to be secure against quantum, is that quantum algorithm for breaking RSA will be much more practical than those, which will be at the limit. Let's say, if you want 64 bits of quantum security, the resources you need for this is much larger than the ones you need to break RSA.
Okay. So thank you so much, André. It was very interesting talking.
Okay. Well, thank you for having me. It was a pleasure.
And yeah, let's stop the recording and have a little chat.
Yeah, okay.
More, right?
Thank you very much.